So number of slides is going to be 300, actually 299. It's going to stay the same for this year. So no plan for updating my slides for part one. But part two, we did not start part two, which is the statistics. Part two and part three, those are like short chapters, and I will cover less number of chapters in part two. Like part two, statistics is chapter 7 and chapter 8, and part three, random processes, which is basically chapter 9 and chapter 10 of the textbook. But I did not follow the textbook quite section by section the way I'm following fundamentals, which is chapter 1 through chapter 5. For part 2 and part 3, I have my own notes, so that's what I will be following. Okay, let's see how far we can cover from chapter 5. Chapter 5, again, so more we are advancing throughout this course, more and more practical topics will come. So in our last class, we did talk about this example, where this example actually is coming from two loaded dice, which means that loaded dice means that two dice, you put one dice here, die 1, and die number 2, and each die has 6 faces, 6 dots, and number of dots is basically is given right here. So for the first die, which is the first argument, number of die is denoted with J, and number of dots facing up for the second die is denoted by K. So I did, because this loaded means that order matters. Die 1 and die 2, this order matters. So which means that if you just simply look at the number of dots, so number of dots for first die could be 2, and for the second die could be one. So this is K, this is J, and for a number of dots for the second die could be 2, and first die could be 1. So that is the reason you see when you see the number of dots 2, 2, that's why you see that 2 quantities are along the diagonal of this table. So that's where the confusion comes. And I did go through the joint range. So joint range, in our last class, I did mention what is joint range. Joint range of these two random variables. So first random variable represents the number of dots facing facing up for the first die, and Y denotes the number of dots facing up for the second die. So therefore, you will see that the joint range elements were 1, 1, 1, 2. We did write already in our last class. I'm just writing it. 1, 6, and then another element is going to be 1, 1. So order matters. So that's why you get 2 quantities. So like that, you see that you fill up this table 2, 1 all the way, and then here you get another quantity. 2. So like that, you see that here you will have 6 times 6, 36, and then you will have 6 extra quantities. That's why you have total 42 elements in the joint range. But if you look at number of dots here, this number of dots remain 36. So here 1 through 6 here, 1 through 6 here. This number of dots here remain 36, but probability changes because of the unfair, which means that in this case it's order. Find the probability of minimum xy, which means that the minimum of number of dots for the first die and the number of dots in the second die. minimum is going to be 3. How to find this probability that this condition satisfies? This probability is basically, look, number of dots for the first die and second die is minimum is going to be 3. So minimum is going to be 3. You start from here. So number of dots for the first die is going to be 3 here, and number of dots for the second die 3. But 3 and 4, minimum of 3 and 4 is also 3. So that's why you would have to add all these probabilities here. So the second component, which is probability that minimum of x comma y equals 3 is going to be, you just keep adding this PMX, this joint PMX along the region that I did mention, which means that joint PMF of random variable x comma y taking value 3 comma 4 plus joint PMF of random variable x comma y taking value 3 comma 5 plus joint PMF of random variable x comma y taking value 3 comma 6 plus joint PMF of random variable x comma y taking value 4 comma 3 plus joint PMF of random variable x comma y taking value 4 comma 5 comma 3 5 comma 3 plus joint PMF of random variable x comma y taking value 6 comma 3. Okay. Now I did miss one element intentionally. Tell me which one did I miss? Intentionally I did miss one. Which one did I miss? Plus joint PMF of random variable x comma y taking values. I did miss intentionally one element here. So I did actually mark all the points here. So it is 3 comma 3. Very good. So it is going to be 1 over 42 for all these elements. So 5 times 1 over 42 plus for this guy it is going to be 2 over 42. So it is going to be 7 over 42. It is going to be 1 over 6. So it's not 5. 1, 2, 3, 4, 5, 6. 6 of them is going to be 6 times 1 over 42 plus 1 of them is going to be 3 is going to be 2 over 42. Is going to be 8 over 42, which is 4 over 21. So this probability that the minimum of x comma y is going to be 3 equals 4 over 21. This is the final answer. Okay. The next one, again, we need to keep this in mind. I need to find the marginal PMX. Marginal PMX. from, again, marginal PMFs you find from joint PMF, joint probability mass function. So given the joint PMF, which is basically, in short, mathematically you can write PMF of random variable x comma y taking value x, y, or jk. Jk equals, it is 2 over 42 when j equals k, and it is 1 over 42 j not equals k. So here jk takes values from 1, 2, 3, dotted, comma 6. So in short, you can write the joint PMF as such. Now, marginal PMF, we have the formula. Marginal PMF of random variable x, which is marginal PMF of random variable x taking value j, which is basically by definition probability that x equals exactly j, which is because we are given joint PMF, which is basically probability that x equals j, y equals anything. So anything means that y can take any value from 1 to 3. So that's why summation is stemming from right here. So you have summation, y could be anything, that's why you sum over k. You sum over k equals 1 to 6. Joint PMF of random variable x comma y, taking value j is fixed, k is value. So in this case, joint PMF of random variable x comma y taking value j comma 1 plus joint PMF of random variable x comma y taking value j comma 2 plus dotted plus joint PMF of random variable x comma y taking value j comma 6. Now when j equals, guys, please pay attention here, when j equals 1, that time only this quantity is going to be 2 over 46. When j equals 2, that time this quantity is going to be 2 over 42. And all other 5 quantities would be 1 over 42. So now when you write the marginal PMF, you write it like that, because you will have to cover all j's here. So marginal PMF of random variable x taking value j equals, you write it like that. Actually, I'm just going to write one more line here. So marginal PMF of random variable x taking value j is going to be one of these quantities, depending on the value of j, one of these quantities will be 2 over 42. So one quantity would be 2 over 42, and rest of the 5 quantities is going to be 1 over 42. So that will give you 1 over 6 for k equals 1, 2, dotted, dotted, all over 6. So that's the result, regardless of the value of j here. J can take any value from 1 to k. So now, because it is marginal PMF, you will have to cover for all j. So what you do, you write it PMF of random variable x taking value j. Marginal PMF of random variable x taking value j is going to be 1 over 6 for j equals 1, 2, dotted, dotted. Six, and it is 0 otherwise. Similarly, if I ask you to find marginal PMF of random variable y, marginal PMF of random variable y. So you write PMF of random variable y taking value k equals, I'm going to directly write the result because you are going to just follow the similar procedure here. So instead of j, you write k. And instead of y equals anything, you will have x equals anything. Instead of k equals 1 to 6, you will have j equals 1 to 6. Just the you just flip the indices. So in that case, the result is going to be the same, 1 over 6 for this time instead of j, you write k equals 1, 2, dotted, dotted, 6 and 0 otherwise. That's it. That's the complete solution of this example. So the main confusion, math is not is quite trivial, but main confusion arises from the lower class. Okay. So the solution that I provide, guys, is very concise and straight to the point. If you write my solution, you write it on a piece of paper, or if you are not writing, I'm okay that you just take your iPad or your phone, take picture. Okay, I'm completely fine with it. Okay? As long as you pay attention. So now we are moving to, so far we talked about joint PMF. Joint PMF for discrete case, for discrete case, discrete random variable case. Now we are going to move on to same thing. So in chapter 3, we talked about PMF, probability mass function, and then we moved on to CDF, which is cumulative distribution function. But because we are dealing with two random variables, instead of PMF, we call it joint PMF. Now we are moving to CDF, but instead of CDF, we call it joint CDF. So we'll talk about joint CDF. So to find joint CDF, actually part of the solution is put it right here. So to find minimum, part of the solution is right here. So joint CDF, to find joint CDF, you define what is the event first. Look, guys, you will understand easily. For single variable, single random variable, what did we do? CDF, single random variable x. CDF we denoted with f sub x, taking value x. It is by definition probability that random variable x takes value all the way up to x. And this x can vary for all x from the entire real line. Okay, so this was for the single variable guy. Just try to match it from single variable perspective, and I have the theory here, but you just pay attention to the main point here. So instead of CDF, I am writing it here, joint CDF. Joint CDF of RV is x comma y. So instead of single variable, we have two random variables. So here you write joint CDF, instead of f sub x, you write f sub x comma y. We are dealing with two random variables. And instead of x, you write x comma y. Instead of probability that x less than or equals x, you use AND operator. Probability that random variable x takes less than or equals lowercase x, comma, and at the same time, and it is and. In other words, intersection, and random variable y less than or equals y, so that you don't get confused. And instead of for all, so this is for all. We call it for all. For all x takes value from the entire real line. In that case, here there are several ways you write. For all x takes value from the entire real line. For all y takes value from the entire real line. In other words, you write it like x, y in the form of a vector. You write it as such. You see the notation here? It's a real line, but in two dimensions. So I wrote it like a vector form. So this is also fine. For all x, y, it's a column vector, takes values from the two-dimensional plane, real line, x, y. So this is the main difference. Now the math part, you will understand the math. Math part is not hard. It is just the notation and how you make use of it. That's all. So let's go right here. So I drew a figure nicely to show the event B. This is the point, any point instead of x, y, I just put x1, y1 to fix it. And this joint CDF basically finds what is the probability of this rectangular region. All the way. Only thing is that there is a gap in the y line, so that is basically, this line is basically y equals y1, and this line is basically x equals x1. Okay? So only thing is that it has two boundaries, and to the left there is no boundary. It goes all the way to negative infinity, and y goes to negative infinity. So y goes from negative infinity all the way to y, and x goes from negative infinity all the way to x1. So this entire region, we call it event B. So this is basically event B. And this event, mathematically, it's a semi-infinite rectangle. So B takes values all the points. See how I read it. B takes values all the points, all the coordinates. All the values such that x less than or equals x1, y less than or equals y. Okay? So when we write the joint CDF, by definition it is probability that x less than or equals x1, y less than or equals y1. Okay? This joint CDF basically finds what is the probability of this event. This joint CDF basically finds the probability of this event, B. So B is written as such. So B, mathematically we write it like that. It is basically a semi-infinite rectangle. semi-infinite rectangle as I visually showed you. So how to find this probability? So by definition, it is joint CDF is basically probability that x less than or equals x1, y less than or equals y1. Now we are going to hear what I say. Like this event consists of all points in the xy plane lying to the left of x1 and below of y1. So when you find the joint CDF, basically, as I said, this comma is nothing but and. Make sure you don't mix up, and I did mention 1,000 times. This comma means and. Yeah. So and means in set theory it is intersection. This and means it is intersection. So basically, you are trying to find, you are determining probability that x less than or equals x1 and at the same time, simultaneously, y less than or equals y. That's all. So the properties, these properties are important. Among all these properties, you will be utilizing this property. Among these 5 properties, you will be utilizing the last property most of the time. Because here you have finite rectangle. So joint CDF is non-decreasing. You remember non-decreasing, I have nice 3D plot, guys. So I will show you how it is non-decreasing. But I'm just trying to link it with single variable. Say f sub x was like this. So this is random variable x. So this is 1 and it goes all the way to negative infinity. At negative infinity, it is 0. Okay? So this is for single variable case. You just extend it to double variable, 2 random variables. In single variable, it is simply a line. For 2 random variables, this y-axis, you have another axis, it is y, and this is x, okay? So now, for 2 random variables, it is going to be out of the page. It is going to be like that. I don't know how I can show you. Anyway, I'm going to show you one example. We'll go through this example, but just for demonstration purpose, I am skipping these slides and going all the way here. Do you see this? So it is from 0, and then it is gradually going up like surface. No? So it is starting from 0 and it is gradually. This is basically a plane. Like you can think of this as a plane. It is starting from 0 and then it is going like that. And at some point, it is going to be flat. You got my point? So that is the whole purpose of showing this joint CDF as a 3-dimensional plot. In most of the books, actually, this 3-dimensional plot, you don't see this 3-dimensional plot, but because of the technology, because of nice Python and nice Python packages, so this year is the first time actually I drew this 3-dimensional plot to demonstrate joint CDF instead of just showing CDF mathematically on piece of paper. So that way you see how CDF looks like. So it is going to be, I don't know, here I cannot. What it is going to be surface like that. surface that goes from negative, goes from 0 and going all the way. Okay. So that's why you see that it is non-decreasing. If any of the arguments of this joint CDF is negative infinity, the value is going to be 0. So it doesn't matter x or y, any of the arguments is negative infinity, it is 0, the value is going to be 0. If both of the arguments go to infinity and to infinity, the value is going to be 1. Okay? And marginal cumulative distribution function, basically from joint CDF, you just bring extract marginal CDF. So marginal CDF of random variable x, you just determine it from the joint CDF. Only thing is that when you determine marginal CDF of random variable x, pass y is infinity. When you determine the marginal CDF of random variable y, make x of the joint CDF infinity. That's all. So the other mathematical term that you see, and for single variable we went through this already. When x, you evaluate x, the limit x tends to a plus, which means that a little more than a, okay? And this joint CDF is basically a continuous function from naught, which means that even though its x goes to a plus, which means a little more than a, but you can evaluate it at a. It's the same thing. Same thing for y, even though y can take any value, y can take value at b plus, which means that a little more than b, but you can evaluate it at b because of the continuous property. And then this is the rectangular property that you can actually, so this is what I'm going to write it here. So if you have if you have a rectangle where, so this is x1, this is x2, and this is y2, and this one is y1. So y can take any value from y1 less than or equals, doesn't matter for continuous case, less than or equals, let's keep less than y, less than or equals y2, and x here can take any value from x1 less than x, less than or equals x2. So you have these two conditions, which means that you are talking about this region. It's rectangular region. And this rectangular region, let's denote it with B. This rectangular region, let's denote it with B. But the probability of this region you can find using the joint CDF. So this is the formula. So you know what is x2, y2, you know what is x1, y1, all these parameters. You can find the probability of this rectangular region. So this is basically B, which is probability of B, which is a rectangle. You can find it using this joint CDF. So these are the properties. Now we are going to go through one example of finding joint CDF. This example is quite big, actually, long example. Let's get started with this. Okay, again, packet switch example. As I did mention, that make sure you pay attention to that example. I'm going to reutilize this example in many of the examples to come. So in this packet switch example, just to recall, packet switch has two input ports, two output ports. At a given time slot, a packet arrives at each input port with probability of 0.5, and is equally likely to be destined to output port 1 or 2. Let x and y be the number of packets destined for output port number 1 and output port number 2, where x, random variable x, random variable y represents the number of packets. Represent the number of packets destined for output ports, port number 1 and 2 respectively. Find the joint CDR. Find the joint CDR for the output ports represented by the number of packets represented by the random variables x and y, which actually denote the number of packets destined for output port number 1 and output port number 2. Find the marginal CDR. So we went through the previous property. We are just directly applying the previous property right here in this example. Find the marginal CDR of what? Okay. So I took this example from the book, but I did modify it to include a few more points. So let's get started with it. Now, do you guys recall what was the joint PMF solution? Given the joint PMF of random variable x comma y. So joint PMF of random variable x comma y in tabular format, do you guys recall? So random variable x comma y can take value x equals 0, x equals 1, x equals 2, y equals 1, y equals 0 actually, y equals 0, y equals 0, this is 1. Y equals 1, y equals 2. I'm going to use red color to denote the joint PMF. When x equals 0, y equals 0, what was the joint PMF? 1 4. 1 4. So when x equals 1, y equals 0, joint PMF was? 1 4. 1 4. When x equals 2, y equals 0, joint PMF was? 160. When x equals 0, y equals 1, joint PMF was 1 4. When x equals 0, y equals 2, joint PMF was 160, right? When x equals 1, y equals 1, joint PMF was 1 8. And that's it, right?
That's it, yeah.
And other values, if I don't write anything, these are impossible events because number of packets cannot be more than 2. So x equals 1, x equals 2, y equals 1, which means here. So this event cannot happen, so therefore probability is 0. This probability is 0. So we have this joint PMF. But we are to find joint CDF. We are to find joint CDF, which is joint CDF of random variable x comma y taking value x y for the entire real plane, two-dimensional plane, which is by definition probability that x less than or equals x comma y less than or equals y equals what? For all values of x can take value from the entire real line, and for all values of y can take value from the entire real line. Okay. So total there are 10 conditions. So I'm going to use yellow. Let's see how does it go. Guys. So I extend this axis. So this is my x-axis, this is y-axis. Y-axis goes from negative infinity to positive infinity. Okay? Negative infinity to positive infinity. And then x can go from negative infinity all the way to positive infinity. Okay? Yeah, try to understand, guys. What matters is these conditions. So x can take value from 0 to 1, 1 to 0 to 1, and 1 to 2, 2, 1, 0. So these values and in between. And y can take value 0, 0 to 1, 1, 1 to 2, 2. And after that, these are impossible events. We don't need. But because we are trying to find the joint CDF, we have to cover the entire real line. You guys remember for the single variable case, we have to cover the entire real line. So here we have to cover the entire real plane. So which means that this region is basically x less than 0, y less than 0. Okay? So this region we have x less than 0, y less than 0. And this region we have y less than 0, x greater than or equals 0. And this region x less than 0, y greater than or equals 0. So let's use this color. Now, somewhat this region is important. So this region is x greater than or equals to y can take any value. And this region is basically y greater than or equals to, and x can take any value from greater than or equals to. Okay, guys, you tell me. So again, math is not hard at all. You just have to understand. You tell me what is the joint PMF right here. So joint CDF. Joint CDF right here. Now, can any event happen when number of packets arrived in the output port 1 is negative? No. So, and number of packets arrived in the output port 2 negative? No. So this guy is going to be 0. So plane starts from flat. So that's why I like to, even though it comes to the end, so that's why this region is 0. Do you see that? This plane is 0. Look at the 3D plot. This plane is 0. And then another, yeah, I'm going to, I'll try to explain the concept, and then the solution will not take much time because you will understand. Okay, when any of these variables is negative, that event is also impossible. Because if x less than 0 and y greater than 0, x less than 0, y greater than or equals 0, x less than 0. So any of these events where number of packets in any of the output ports is negative, that is going to be 0. So that's why this region, your joint CDF is going to be 0. This region, your joint CDF is going to be 0. Okay? But you will have some joint CDF right here, and then it's going to be discrete surface, they will keep going up. Okay? So you will see some joint CDF right here, you will see some joint CDF right here, 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 and so on. So we'll go through all these conditions. Now, condition number 1. So now I'm just going to fly given the conditions. So solution. Oh, I did write the solution already. Conditions. One, if x less than 0 or any of them, or and y less than 0. Okay. So you write joint CDF. Yes, I'm not writing joint CDF because you guys already know I defined it. X comma y, taking value x comma y, because we have these conditions, and by definition it is by definition probability that x less than or equals x, comma, y less than or equals y. Okay, so it is going to be 0. Second condition you have, if 0 less than or equals x less than 1 and 0 less than or equals y less than 1. So we are talking about this region. 0, 0 to 1 but not including 1, and 0 to 1 here y not including 1. So we are talking about this region. So the only joint PMF that you see is valid is 1/4. Okay? So this 1/4 corresponds to value x equals 0, y equals 0. So in that case, we can find f sub x comma y taking value x, y is by definition probability that x less than or equals x comma y less than or equals y. And the only joint PMF that this condition satisfies is basically joint PMF of random variable x comma y taking value x equals 0. In terms of joint PMF. So it is x equals 0, y equals 0. So this is basically 1/4. Okay. So this condition gives you 1/4. And that's why this condition gives you 1/4. That's why in my nice 3D plot, you see that this blue color, do you see, does it look like it's a 3D plot? You see that it's lifted up, right? It's lifted up a little bit, 1/4. So this surface is basically 1/4, 0 all the way to 1, but not including 1. So that is the region I'm talking about. All right, guys, you take 5 minutes break, and then we'll complete this.